Welcome to the third lecture on the series of lectures on fluid inclusions in minerals. We have so far got a brief introduction about what these fluid inclusions are, and have looked into the mechanism that can be visualized for the entrapment of these tiny fluid cavities within the growing crystal, and this primarily correspond to the fluid, the parent fluid, which gets entrapped within the growing crystal when the crystal grows from the fluid medium or is recrystallizing in presence of a fluid. Essentially, it is a fluid present situation and corresponds to a close time relationship, or we can say that the same time at which the inclusions are getting entrapped is exactly the time at which the crystal is primarily growing. Now, we will see if we remember while defining these fluid inclusions, we said that these inclusions are tiny cavities within the minerals that form either during the primary growth of the mineral or any time afterwards. So, now we will just have to look in terms of the mechanism, of course, remain the same, that the inclusions will be entrapped or encapsulated within the crystal lattice. But here, so once a single crystal that we have visualized, or in case of a polycrystalline aggregate that we described through the sketches. So, here we can visualize that the crystal or the particular mineral vein, say for that matter, has already formed as a polycrystalline aggregate, and then if this particular polycrystalline aggregate is deformed later on, and this essentially has to be a brittle deformation. So, that deformation, suppose then looking at this particular diagram, this particular diagram depicts the very first stage in which if this represents a single crystal, then there is a fracture in that crystal, and the fracture space is again filled up by fluid. This fluid could possibly be not at all related to the fluid which originally formed this particular crystal. Now, if this process is also operating somewhere in the subsurface at pressure temperature conditions which are different from operating on the surface, the only point is that the processes that will operate on the surface will be far more slower and under that kind of a condition we cannot expect much of minerals to form or recrystallize, even though it is not 0. So, imagine a situation. So, then this particular fluid within the fracture space has also started to interact with the host mineral, and then deposit the same material of the host mineral on the fracture, which we can say that the fracture is basically getting healed. Now, this particular fluid will interact with the crystal and will get by virtue of it the chemistry of it, and will start healing up this particular fracture, and this the subsequent diagram, and here it shows the progressive stages by which this particular fluid is healing up this fracture, and finally we see that this which was essentially a fracture, after it gets healed up, it is left with numerous tiny such inclusions as fluids which also are inclusions and have the same characteristic more or less in terms of their optical characteristic, as we will see later, same as the inclusions which are trapped during the primary growth of this mineral. So, just for your so this same quartz crystal, suppose there is a fracture that is created. If we say that this particular quartz grain is just fractured, and within that fracture space fluid is got in, and this particular fracture has been healed and tiny inclusions are entrapped, and if we take a section from this particular quartz here, we are taking a section which is that we discussed before, which is about 300 micron in its thickness, and observe under the microscope. Okay, so if we take a section from this quartz, suppose there is a fracture over here, and we are taking a section from this particular quartz, then what we will see here is that when we see them under the microscope, we see these inclusions which are arranged in a linear trail, compared to what is the situation here when these inclusions which were trapped during the primary growth of this particular crystal, and those inclusions were trapped randomly at any particular anywhere within the growing crystal in its lattice. And to differentiate between the two, if we take a section of this particular crystal, same section kind of is a wafer, then if we see under the microscope, then we will see the inclusions which will be and we, since they are present as different depths from the surface, because this particular thing is a 300 micron thick slice doubly polished wafer, and these inclusions will get focused at different depths, but randomly within the field of view. Here the situation is that these inclusions will not be focused randomly on the field of view, but they will be aligned with respect on a linear array, and this linear array will apparently move depending on the suppose this is the fracture, and when we are taking a section of this, so this particular this fracture is inclined in this manner, and when we see them under the microscope, raise or lower the stage of the microscope, this particular trail moves either way depending on whether we are raising or lowering the microscope stage. So this is one example. This particular photograph has been taken from literature from as shown here. So this mechanism of formation of these inclusions after the growth of the host mineral by healing the cracks or the fractures which are created within the mineral or the polycrystalline aggregate is now very well demonstrated or very well supported by synthetic fluid inclusion experiments, where what we see here on this particular left side of the diagram is essentially the inclusions which were trapped in the laboratory, and this entrapment process is brought about by taking inclusion free quartz, creating fractures in them, and then putting them into an apparatus which are the hydrothermal apparatus, where taking fluid of desired composition and almost this is mimicking the natural condition of healing the fracture of the mineral, and in this process trapping the fluid inclusion. So what we can see here within this is an example of the synthetic inclusions which are essentially trapped by the same mechanism of healing of the fracture, and this is an example of fluid inclusions in fluorite, where this represents a fracture plane which is almost parallel to the surface of the wafer on which we are examining, and we see a very large number of such inclusions being focused at the same plane. And okay, so this is essentially what can be explained in this way. So the fractures, so this is suppose a block of a polycrystalline aggregate, and this could undergo the fracturing. This is a fracture, and fluid will percolate through this particular fracture space. This fracture is very unlikely to be occurring in just in isolation. There could be many such parallel fractures, or could be, depending on how the fracture is generated, could be there are some conjugate sets of fractures also that could have taken place in this particular polycrystalline aggregate. So, now when we see them under the microscope, we see this is an example of one particular grain, a particular polycrystalline aggregate of quartz, where we could see that this fracture. So, what is seen here, these are the parallel sets of fractures, and even we could see even intersecting sets, and all these are essentially populated by these tiny inclusions, and this is how we see them. For example, coming to the same diagram, where we had this fracture and maybe parallel sets of fractures or intersecting sets of fractures. So, if we see them under the microscope, and these will be the quartz grains. Suppose this is a aggregate of quartz. So, what we see here is that these kind of fractures will always be transgressing, or actually will be transgranular, that means traversing through many such grains of the minerals, and these will define what actually will be the trails, which we will call them as the intergranular trails. And within which we will see that there are numerous inclusions which will be observable, and exactly the same way that I just described, that we see under the microscope, we see the inclusions very much arranged in linear arrays, and those kind of arrays they move when we raise or lower the microscope, and some of such kind of features will be better seen through videos which we will be posting. And as against that, it could also so happen that if we have this mineral this is the aggregate of the section that we have taken from the sample of quartz. Sometimes we might see that there are fractures which are just terminating within one grain, within the single grain of this particular host mineral, and we are seeing inclusions within this particular trail. So, these two situations actually represent two different conditions. In the first case, where the fractures or the cracks are transgranular and traversing through many of these grain of the host minerals, there we are very sure that the particular fracturing took place after the formation of the vein, after the formation of the polycrystalline material that we are seeing, for example, our quartz vein. Now, when we see such kind of a situation, it gives us an idea that it could be a situation where this concomitant fracturing and mineral growth that was taking place in formation of a vein, as we illustrated earlier, it might have so happened that the earlier stage of quartz grains which were forming and were subjected to fracturing, and later stage of fluid has only just made the quartz grains overgrow on the existing quartz grains. So, such kind of a situation is likely to occur. So, we might get such situations where there are fracture spaces, but the fracture spaces or the trails containing these inclusions are just terminated or just truncated or within the grain itself, not traversing the many of these grains. So, these kind of situation depict three different situations. three different conditions origin of this entrapment of these inclusions, and we have not yet introduced the exact term by which we actually call the three situations. In a first situation where the inclusions are actually a part of the random three dimensional network, where they will get focused on different planes just randomly when we see them under the microscope. The other situation is that they are aligned in transgranular healed cracks in the mineral aggregate, and the third situation is that they are arranged in healed cracks, but not traversing through many grains, so that they are not transgranular in nature, but rather they are intragranular. One of the possibilities of some such kind of an intragranular fracture could also result from, for example, if there is a fracture that is taking place and this fracture has just been transgressing through some of the grains, but actually truncated at some of the, because a fracture is when it's looking at a micro scale, if it has to truncate or it has to die out at some point, then it also might. So, and one thing also we have to remember that what we are seeing while examining the fluid inclusions under the microscope, that we are making only a two dimensional view of what the things are in three dimension. So, sometimes it might so happen that a fracture which was actually traversing through many grains like this one here would have terminated here within one particular place up beyond which the fracture did not propagate, and we happen to take a section just where that we could see the fracture within this particular grain. So, in that case it could be a situation where it needs a proper evaluation that whether such kind of situation is because of a intragranular or intergranular healed cracks. Here also there are some 2 or 3 illustrations which would make it clear, depending on. So, we could have such kind of the middle figure, even this figure also, here there are, we could see that very nicely arranged subparallel trails in which we could see fluid inclusions of variable sizes. Here the micron bar is 20 micron, here it is mentioned. So, we can imagine that. So, first thing that we learn from here is that when this kind of, supposing that this particular healed crack is transgranular or intergranular, and it is given rise to entrapment of the fluid inclusions by healing of this particular crack. So, it generally results in inclusions which will be very much variable in their size. Similar is the case here, and one such fracture which looks to be terminating at this point. So, then this raises the possibility that whether we could categorize into a third category that particular this fracture also, even though they are at a high angle to each other, they seem to be terminating at a particular point here. And this is the example also that we have this kind of a heel crack. Within that heel crack, we see that there are inclusions which look to be very regular shaped and perceptibly a large size inclusion, where we could identify, and in a population of much smaller other inclusions. So, therefore, as regards to the origin of these inclusions, the mechanism that we have seen, they are essentially arise out of the growth irregularities, imperfections during the growth of the crystal. When we are talking about the primary growth of the crystal from the fluid medium, there are situations in which the fluid inclusions also can be entrapped within a mineral after its formation and its formation anywhere in the subsurface in the form of a vein or any matrix mineral in a particular rock. So, they can be subjected to later deformation, and brittle deformation like fracturing will always allow later fluid to percolate through it, and these situations are sometimes could be very close, operating at a pretty close temporal spectrum, or they could be separated in time very conspicuously or substantially. In that case, the characteristics of the fluids occurring as inclusions for the first category or the inclusions of the thing that we are considering here in heel cracks, they could be different. So, here are also a good example of how such kind of trails, intersecting trails containing population of inclusions is shown here. Here the sizes of the inclusions are also quite different. Okay, so now we will go on to discuss. We go a little bit close to these fluid inclusions in minerals, and we see their optical characteristics, how we can identify them. When we see them under the microscope, it of course requires a bit of practice, and after which getting a bit of an acquaintance or a longer period of observing and looking at them, and then still we can describe these inclusions based on the optical characteristics which is observable. Okay. Now, we will be considering different types of inclusions that we see in minerals in general. What we see here is an example, is a sketch, a representative sketch of what we say is a aqueous biphase inclusion. So, this actually is a liquid, and the object which is at the central part is the vapor, and this particular inclusion is actually a aqueous biphase inclusion. Even though at the very first instance one can always ask that how do I know that it's an aqueous liquid and vapor. So, if we first make a tentative identification, let us say that yes, it is an aqueous biphase inclusion. This is the liquid part, this is the vapor part. So, what do we observe here, and these inclusions will always be very distinct optically, because they are within the solid host and the surrounding of that particular. So, if we define this particular black line as the inclusion wall, and so this means surrounding of it is the solid crystal, and the refractive index of there is a refractive index contrast between the solid host and the material which is inside, which is liquid. So, it is quite obvious that this refractive index contrast will always make them very distinct optically when we see under the microscope in transmitted light. So, what we see here, that is a vapor, but characteristically we see that this vapor is surrounded by a dark rim. This particular dark rim could be of variable width, as we will be seeing them later. So, now even though it is not of a very important consequence, but we always we should be knowing that why this typical aqueous biphase inclusion has an appearance like this. We will see them, already have seen them some examples, and we will see them some more. So, what exactly happens here, that this particular, taking a very regular shaped, suppose this is an exaggerated view of an inclusion which is roughly spherical in its shape, and it has, and this part is the water, is the liquid. Liquid means we always refer to watery liquid, and then this part is a vapor. Now, this liquid and a vapor also have a contrast in their arrays. The liquid will have a higher array than the vapor, and we are putting this inclusion, we are seeing this inclusion in the solid host where we have a wafer, and this wafer is the below surface is here, and light is coming from the light source of the microscope in a transmitted light, and when the light enters into this particular inclusion, since there is a Ri contrast, so the light most of the part here will be perpendicular to the interface of the liquid and vapor, because the light is going from a denser to a rarer medium, it's always will be refracted away from the normal, and so this particular bunch of rays which will be near perpendicular to the vapor liquid interface will actually be able to pass through without much of deflection, whereas those which will be falling at a gradually higher and higher angle on the liquid vapor interface will experience refraction, and when the angle will exceed the critical angle, they will not be able to pass through and will be undergoing total internal reflection, and that will explain. So a part of this particular vapor bubble from where there won't be any light, that will be the light will not be able to penetrate through some part of this, and when we see them under the in a 2-dimensional view of this particular inclusion, we see them in the microscope, they will have a look that the vapor will always be invariably be surrounded by a dark rim, whose the dark rim thickness of the width of the dark rim will vary. Let us have a example of what exactly we have demonstrated here. This is the inclusion. So here this inclusion is in a quartz, sample of quartz, and in this quartz we could see the solid the host mineral, and the surrounding part is a host mineral. So there is an Ri contrast. So this is the host mineral quartz. Well, there are other inclusions are also distributed, and this is the inclusion cavity, and this inclusion cavity we could see that this is the vapor, and the central part of the vapor is bright, surrounded by a dark rim, which exactly we just explained now, and because of some of the light also just being totally internally reflected and passing through this liquid, so this liquid also has a brighter appearance just surrounding the vapor. And so this is one example. This is also another. This is another example. Here also we see that this is another inclusion, and this micron bar is 20 micron. So you can imagine, we can always estimate the width or the maximum dimension of this particular inclusion, which would be around 12 to 15 micron in this case, and the similar case here, these two inclusions are of different shape. Now looking at this inclusion will make our, so it depends on how this particular inclusion geometry is. If the inclusion geometry is of a regular shaped inclusion, regular shape, and then the vapor bubble is exactly occupying the top surface part the way we have described here, but there can be many variation depending on the ratio, when the proportion of the vapor bubble to the inclusion total area of the total volume of the inclusion, and the way the if it happens to be a flat kind of an inclusion where the vapor bubble also is kind of occupying a kind of a flat geometry, then the dark rim around the vapor bubble will all be very thin, and situations corresponding to this where the vapor bubble is perfectly spherical, there the dark rim will be much wider. Again, so we have to keep it in mind that we are not able to see the third dimension when we are examining them under transmitted light. We can only just have a can see their the shape and the size, as you can measure in 2 dimension, can represent in terms of a maximum dimension, or if it happens to be a regular circular shape, we can tell in terms of the diameter. And the bubble, in most of the cases, invariably the bubble will have a circular outline, though it may be different depending on the inclusion geometry, and sometimes also in many of the instances, as we have seen, that this particular vapor bubble sometimes executes a little bit of a random movement, which mimics the Brownian movement in molecules in gas. So, that is why it is termed as a pseudo Brownian movement, and there are many other characteristics of this kind of fluid inclusions as we see them under transmitted light and their optical characteristics. We will continue discussing on this topic in the next class. Thank you.